Good evening, and welcome to The Gentle Scientist. Tonight, we drift into the vast and ancient embrace of the Pacific Ocean, the largest body of water on Earth, deeper than mountains are tall, older than the continents themselves. Long before humans named the seas or drew maps of distant shores, the Pacific was already here and holding secrets in depths no light has ever touched. This is an ocean so immense that all the land on Earth could fit within its boundaries and still leave room for more water. It stretches from the frozen coasts of Antarctica to the Bering Sea, from the coral atolls of Polynesia to the volcanic shores of the Ring of Fire. Beneath its surface lies a world of mountains taller than Everest, trenches deeper than any canyon, and creatures so strange they seem borrowed from dreams. Tonight, we will journey across this endless blue. We will descend into trenches where pressure crushes stone, rise to volcanic islands born from fire, and drift alongside creatures that glow in the darkness. We will trace the paths of ancient navigators who crossed half the world guided only by stars, and feel the currents that connect every shore in an invisible web of motion. We will discover how this single ocean shapes weather across continents, holds the memory of Earth's climate written in sediment, and continues to reveal mysteries that remind us how much remains unknown. If you find peace in these quiet explorations, I invite you to like this video, subscribe to The Gentle Scientist for more journeys into the natural world, each one crafted to calm your mind and cradle your thoughts as you drift off. And if you'd like, take a moment and leave a comment below. Tell me where you are listening from. What time is it there? Are you beside an ocean, or are you far inland, dreaming of distant waves? I love knowing that we are connected across this world. For now, let yourself settle. Let your breathing slow to match the rhythm of gentle swells rising and falling across an endless sea. Close your eyes if they grow heavy. Let the Pacific ease your thoughts and soften the edges of your mind. We begin our journey now, together. Let's drift into the vast and beautiful mystery of the Pacific Ocean, where everything begins and everything returns, and where, tonight, you will find rest. Are you ready? Let's begin. The Pacific Ocean is so vast that the word ocean itself feels too small to contain it. If you were to gather every piece of land on Earth, every continent, every island, every mountain range and desert, and place them all within the Pacific's boundaries, they would fit entirely within its embrace, with room left over for more water still. This single ocean covers nearly half the surface of our planet, stretching across more than 60 million square miles of Earth's curved face. Stand on the western shore of North America and look out toward the horizon. Somewhere beyond that line where sky meets water, beyond the curve of the Earth itself, lies Asia. Between those two shores stretches an emptiness so profound that early explorers feared they might sail forever and never find land again. The distance from Panama to the Philippines is greater than the entire width of the Atlantic. It is greater than the circumference of the moon. To cross it by ship takes weeks. To fly over it takes half a day. And beneath the surface, in the depths where light fades to absolute darkness, that vastness multiplies into something even more staggering. The average depth of the Pacific is more than 2.5 miles. Imagine standing at the rim of the Grand Canyon and looking down. Then imagine stacking another Grand Canyon on top of that, and another, until you've built a tower of canyons reaching upward into the sky. The Pacific, turned on its side, would swallow them all. In some places, the ocean floor drops even deeper. For every 10 meters you sink beneath the surface, the pressure rises by 1 atmosphere. At 30 meters down, where recreational divers venture, the pressure is 4 times what we feel on land. At 100 meters, it is 11 times greater. At 1,000 meters, a depth still far short of the sea floor in most places, the pressure is 100 times what our bodies were designed to withstand. And still the ocean descends, deeper and deeper, into realms where the very concept of pressure becomes difficult to comprehend. Yet for all this force, for all this weight of water pressing down through miles of darkness, the Pacific does not feel violent or harsh. Stand on its shore during a calm evening, and it stretches before you in perfect stillness. The surface reflects the sky like polished glass. Small waves lap gently against sand, their rhythm so steady and ancient that it seems impossible they could ever stop. The ocean breathes. It rises and falls with the pull of the moon, with the turning of tides that have kept the same rhythm since before mountains existed. There is peace in its vastness, a kind of gentle infinity that quiets the mind simply by existing. The ancient Polynesians understood this vastness in ways that modern people can barely imagine. They built great double-hulled canoes and ventured into the Pacific's emptiness, armed with nothing but knowledge passed down through generations. They read the stars like maps written in light. They felt the subtle swells that revealed the presence of distant islands over the horizon. They watched the flight patterns of birds and the colors of clouds, the taste of the wind, and the temperature of different currents. With these signs alone, they crossed thousands of miles of open water, finding tiny specks of land in an ocean so immense that missing your destination by even a few degrees would mean sailing past it into emptiness, never to return. These navigators discovered that the Pacific, for all its size, was not empty. Scattered across its expanse lie more than 25,000 islands. Some are large enough to hold nations. Others are merely coral atolls, rings of reef barely breaking the surface, encircling lagoons of the clearest blue water imaginable. When you look at a globe and truly see how much of it is Pacific blue, something shifts in your perspective. The continents begin to look like interruptions in the ocean, rather than the ocean being spaces between lands. You realize that Earth might more accurately be called the water planet, and that the Pacific is the most perfectly realized expression of that identity. The weight of all this water is almost incomprehensible. Scientists estimate that the Pacific holds more than 600 million trillion tons of water. That number is so large that it becomes meaningless to the human mind. Try to imagine it this way instead. If you could somehow remove all that water and measure it, you would find that it represents more than half of all the free water on Earth's surface. Every river, lake, ice cap, and other ocean combined would still be less than the Pacific alone. All that water presses down on the seafloor with immense force, and the seafloor presses back, held up by the mantle beneath. This balance, this conversation between water weight and geological resistance, has remained stable for hundreds of millions of years. The Pacific Basin is a vast bowl carved into the planet's crust, and it holds its water with the patient strength of stone that has learned to yield without breaking. The Pacific Ocean is not merely vast. It is ancient beyond the reach of human memory, older than any landscape you have ever walked upon. While mountains rise and crumble, while rivers carve new paths and continents drift across the globe, the Pacific endures. It is the oldest ocean basin on Earth, a body of water that has maintained its essential identity for longer than almost any other feature on the planet's surface. To understand the Pacific's age, you must first understand that oceans are not permanent. They are born, they grow, they age, and eventually they close, swallowed back into the earth as tectonic plates collide and seafloor sinks into the mantle. The Atlantic Ocean, for instance, is young, still widening as the Americas drift away from Europe and Africa. The Mediterranean is ancient but shrinking, destined to disappear as Africa pushes northward into Europe. But the Pacific has been here through it all, witnessing the birth and death of other seas, persisting through transformations that have completely rewritten the map of the world. The story begins more than 200 million years ago, during a time when all of Earth's continents were joined together in a single massive landmass called Pangaea. If you could have stood on the eastern shore of that supercontinent and looked out across the water, you would have been gazing at Panthalassa, the all-ocean, a body of water even larger than today's Pacific. Panthalassa covered more than 70% of Earth's surface, a global sea that wrapped around Pangaea like an endless embrace. As Pangaea began to break apart, driven by heat rising from deep within the planet, the pieces drifted in different directions. The Atlantic Ocean opened as a narrow rift between the separating continents, growing wider with each passing million years. Other seas formed and vanished. But Panthalassa, that ancient super ocean, transformed rather than disappeared. It became the Pacific, shrinking somewhat as new land rose around its edges, but never closing, never surrendering its fundamental character as the planet's greatest reservoir of water. The Pacific ocean floor itself tells this story in layers. Beneath the waves, hidden from sight, lies oceanic crust that has been dated to nearly 200 million years old in some regions. This is extraordinary because oceanic crust is constantly being recycled. At mid-ocean ridges, new crust forms as magma rises from the mantle and cools into solid rock. That rock then spreads outward like a conveyor belt, traveling slowly across the seafloor until it reaches a subduction zone, where it bends downward and sinks back into the Earth's interior, melting and rejoining the mantle from which it came. This process means that most oceanic crust is young, geologically speaking. The Atlantic seafloor, the youngest major ocean, has crust that dates back only about 180 million years at its oldest edges. The Pacific, however, contains some of the oldest oceanic crust in existence, preserved in certain areas where the conveyor belt moves slowly and subduction has not yet consumed it. To stand on a ship above such ancient seafloor is to float above stone that was cooling into solid form while dinosaurs walked the earth, while the first flowering plants were just beginning to spread across the continents. The water itself is even older than the basin that contains it. Water molecules are among the most durable things in nature. They cannot be destroyed by ordinary processes. They can freeze into ice or evaporate into vapor. They can be absorbed by living things or locked inside minerals. But the molecules themselves persist. The water in the Pacific has been cycling through Earth's systems since oceans first formed more than 4 billion years ago, when the young planet cooled enough for rain to fall and collect in low-lying basins. Some of the water molecules in the Pacific were once part of ancient seas that covered entirely different landscapes. They evaporated under prehistoric suns, fell as rain on continents that no longer exist, flowed through rivers that have long since vanished, and returned to the ocean again. They have been inside the bodies of trilobites and dinosaurs, inside the first fish to venture onto land, inside the trees of Carboniferous forests and the grasses of Ice Age steppes. Every drop of Pacific water has a history longer than geology can fully trace. When you swim in the ocean, when you taste its salt on your lips, you are touching something that has been part of Earth's story since the beginning of the story itself. The salt dissolved in that water came from rocks, weathered over billions of years, minerals carried to the sea by rivers, and concentrated by endless cycles of evaporation. The sodium and chloride ions that make seawater salty have been in solution so long that they have circulated through every ocean basin that ever existed, accumulating slowly until the seas reached their current salinity. The Pacific witnessed the age of the dinosaurs in ways no human ever could. For more than 150 million years, as those great reptiles dominated the land, the Pacific surrounded the continents where they lived. When asteroids fell into its waters, they created impact craters on the seafloor and sent tsunamis rolling across its entire width. When volcanic islands rose from their depths, they provided stepping stones for marine life to spread across the ocean. When the climate changed and sea levels rose or fell by hundreds of feet, the Pacific's shorelines shifted across the continental shelves, drowning river valleys and exposing new land. The ocean remembers all of this, not in any conscious way, but in the sediments that accumulated on its floor, layer upon layer, each one a page in the longest book ever written. Scientists who study these sediments can read the history recorded there. They find the shells of microscopic organisms that lived in surface waters millions of years ago and settled to the bottom when they died. The chemistry of those shells reveals the temperature of ancient seas, the amount of oxygen in the atmosphere, even the configuration of continents and the strength of ocean currents. In certain layers, they find elevated levels of iridium, an element rare on Earth's surface but common in asteroids. These layers mark moments of catastrophic impact, including the event 66 million years ago that ended the age of dinosaurs. The asteroid fell into what is now the Gulf of Mexico, but the Pacific felt the consequences. Tsunamis raced across its surface. Debris ejected into the atmosphere fell as a global rain of fire. Darkness followed, and when light returned, the world had changed forever. Yet the Pacific endured, as it always has. The extinction that wiped out 3/4 of Earth's species left the ocean itself largely intact. New life evolved to fill the empty niches. Whales, which did not exist before the extinction, eventually emerged and took to the seas, becoming the largest animals ever to live. The Pacific welcomed them, as it has welcomed every form of life that adapted to its waters. The ocean also witnessed the slow transformation of the planet's surface. It watched as India, once an island continent drifting alone, collided with Asia and thrust up the Himalayan mountains. It felt the tremors of that collision through the seafloor, transmitted as seismic waves that rippled through rock and water alike. It adjusted its currents as the new mountains altered wind patterns and changed the distribution of rainfall across the continents. It saw the rise of the Andes as the Nazca Plate, a section of Pacific seafloor, dove beneath South America and melted, generating the magma that built those mountains from below. The Pacific literally sacrificed portions of itself to create new land, its crust sinking into trenches and re-emerging as volcanic rock on continental shores. This process continues today. Every year, a few more centimeters of Pacific seafloor disappear into subduction zones, while new crust forms at mid-ocean ridges to replace what was lost. The water molecules in the Pacific have also been part of Earth's ice. During the great ice ages of the Pleistocene, when glaciers advanced across North America, Europe, and Asia, enormous amounts of water were locked up in ice sheets miles thick. The sea level dropped by more than 300 feet. Coastlines that are now underwater became dry land. The Pacific shrank, but did not disappear. And when the ice melted, as it has done several times in Earth's recent history, the water returned to the ocean, raising sea levels again and drowning the valleys and plains that had briefly been exposed. Some of the water in the Pacific has been frozen and melted dozens of times over the past few million years. It has been part of icebergs calving from glaciers, part of winter snowfall on mountains, part of the vast ice sheets that covered entire continents. Through all of these transformations, it eventually found its way back to the ocean, flowing down rivers or melting directly into coastal waters, rejoining the great reservoir from which it came. The Pacific is not a static pool. It is a living system, constantly exchanging water with the atmosphere, with rivers, with ice caps, and underground aquifers. Yet through all this exchange, through all the cycles of evaporation and precipitation, of freezing and melting, the ocean persists. It maintains its identity across timescales that make human civilizations seem like brief flickers of light. The ancient peoples who lived along Pacific shores understood this in their own way. They saw the ocean as eternal, as something that had always been there and always would be. Their creation stories often featured the ocean as the primordial element from which all else emerged. In Polynesian cosmology, the ocean existed before the sky, before the land, before even the gods themselves. Modern science, approaching the question from a different direction, arrives at a similar conclusion. The ocean was indeed among the first features of the Earth to form after the planet cooled enough to support liquid water, and it will likely be among the last to disappear billions of years from now when the sun grows hot enough to boil away Earth's seas entirely. Beneath the Pacific's surface lies a landscape more dramatic than any found on land. If you could somehow drain away all the water, if the ocean floor were revealed to the open air, you would see a world of staggering scale and beauty. Mountains taller than Everest rising from abyssal plains. Valleys deeper than the Grand Canyon cutting through the seafloor. Volcanic peaks stretching in chains for thousands of miles. Cliffs that drop sheer for miles into darkness. This hidden topography shapes everything about the Pacific, from the currents that flow through it to the life that flourishes in its waters. The most dramatic features of this underwater world encircle the Pacific like a crown of fire and stone. Around nearly the entire perimeter of the ocean runs a boundary where tectonic plates meet, collide, and grind against one another. This boundary is called the Ring of Fire, and it is the most geologically active region on Earth. More than 75% of the world's volcanoes line this ring. More than 90% of Earth's earthquakes occur along its length. It is a place where the planet's inner heat finds release, where the slow movements of the mantle express themselves in sudden, violent ways. The Ring of Fire exists because the Pacific Plate, the massive section of oceanic crust that underlies most of the ocean, is surrounded by other plates moving in different directions. Along the western edge of the Pacific, the oceanic plate dives beneath Asia and the island chains of the western Pacific, creating deep trenches and volcanic arcs. Along the eastern edge, it collides with the North American and South American plates, building mountains and triggering earthquakes. In the south, it meets the Australian and Antarctic plates in a complex zone of spreading ridges and transformed faults. These boundaries are not smooth or gentle. They are zones of immense stress where the Earth's crust buckles, breaks, and melts. When one plate slides beneath another in a process called subduction, the descending rock is forced downward into the mantle where temperatures and pressures rise. As it descends, water trapped in the rock is squeezed out. That water lowers the melting point of the surrounding mantle, causing rock to melt and rise as magma. This magma eventually finds its way to the surface, erupting as volcanoes that build islands and mountains along the edge of the overriding plate. This process has created some of the most spectacular volcanic landscapes on Earth. The islands of Japan, the Philippines, Indonesia, and Papua New Guinea all owe their existence to subduction occurring offshore. The Aleutian Islands, stretching westward from Alaska, form the same way. The Andes Mountains, running the length of South America, rose as the Pacific seafloor dove beneath the continent, melting and generating the magma that fed countless volcanoes. Even the Cascade Range in the Pacific Northwest, home to Mount Rainier, Mount Hood, and Mount St. Helens, exists because of subduction happening just off the coast. But the Ring of Fire is only the most visible expression of the Pacific's hidden topography. Beneath the waves, scattered across the ocean floor, lie thousands of seamounts, underwater mountains that never quite reach the surface. These volcanic peaks rise from the abyssal plains like monuments to ancient eruptions. Some stand more than 10,000 feet tall, their summits still thousands of feet beneath the surface. Others come within a few hundred feet of breaking through into air and sunlight before erosion and subsidence pull them back down. Many seamounts began their lives as volcanic islands. They formed over hot spots, places where plumes of hot rock rise from deep in the mantle and burn through the oceanic crust like blowtorches. As magma erupts repeatedly from the same spot, it builds a mountain that eventually breaks the surface and becomes an island. But the tectonic plate above the hotspot is moving, carried along by the convection currents in the mantle below. Gradually, the island drifts away from its source of magma. The volcano goes dormant. Wind and rain begin to erode the exposed rock, and slowly, over millions of years, the island sinks back beneath the waves as the cooling seafloor contracts and subsides. The Hawaiian Islands tell this story perfectly. The Big Island of Hawaii sits directly above a hotspot and hosts active volcanoes, still building the island higher. But northwest of Hawaii, a chain of older islands stretches away across the Pacific. Each island in the chain is progressively older and smaller, worn down by erosion and sinking as the seafloor beneath it ages. Eventually, the chain becomes a string of seamounts, former islands now completely submerged, marking the path the Pacific Plate has taken over the hotspot during the past 70 million years. If you could explore these seamounts, diving down through the water column to reach their peaks, you would find ecosystems clinging to the rock, corals that prefer the cooler temperatures of deeper water, fish that gather in the currents forced upward by the mountain's presence, predators that come to hunt where prey concentrates. Each seamount is an oasis in the desert of the abyssal plain, a place where life finds purchase on stone rising from the depths. Among all the mountains hidden beneath the Pacific, one stands supreme. Mauna Kea, which forms part of the Big Island of Hawaii, is often described as the tallest mountain on Earth. This seems impossible at first. Its summit stands only about 13,800 feet above sea level, far shorter than Everest's 29,000 feet. But this measurement ignores more than half of the mountain. Mauna Kea rises from the floor of the Pacific, which lies more than 19,000 feet below the surface. Measured from its true base to its summit, Mauna Kea stands more than 33,000 feet tall, nearly 1,000 feet higher than Everest measured from sea level to peak. To stand on the summit of Mauna Kea is to stand atop a mountain that has grown from the sea floor over hundreds of thousands of years, built by countless eruptions, layer upon layer of cooled lava stacking higher until finally breaking through the ocean surface. The journey from seafloor to summit spans every environment the ocean contains. The base sits in perpetual darkness and near freezing temperatures. As you ascend, you pass through zones where strange fish hunt in the twilight, where sperm whales dive to chase squid, where light begins to filter down from above. Finally, you break through into the surf zone, and then into air. The summit of Mauna Kea now hosts astronomical observatories, their domes gleaming white above the clouds. Scientists chose this location because the air there is extraordinarily clear and stable, perfect for telescopes that peer into the depths of space. There is poetry in this. From the top of a mountain that rose from the ocean's deepest places, humans look outward toward the farthest reaches of the universe, using a peak built by the Earth's inner fire to study the light of distant stars. But if the Pacific holds mountains taller than Everest, it also contains chasms deeper than any mountain is high. Along the western edge of the ocean, where the Pacific plate meets other plates and dives beneath them. The seafloor bends downward into trenches that plunge miles below the surrounding ocean floor. These trenches are the deepest places on Earth's surface, valleys so profound that if you placed Mount Everest at their bottom, its peak would still be more than a mile underwater. The deepest of all is the Mariana Trench, an arc-shaped depression in the western Pacific near the island of Guam. This trench stretches for more than 1,500 miles and reaches depths that challenge human comprehension. At its deepest point, called the Challenger Deep, the seafloor lies nearly 7 miles beneath the surface. The pressure there exceeds 8 tons per square inch, more than 1,000 times the atmospheric pressure at sea level. It is a pressure that would instantly crush anything not specifically designed to withstand it. Despite this crushing pressure, despite the complete absence of sunlight, despite temperatures barely above freezing, life exists in the Challenger Deep. In 2012, filmmaker James Cameron descended alone in a specially designed submersible called the Deep Sea Challenger. He became only the 3rd person ever to reach the deepest point in the ocean, and the first to spend any significant time there. Through the submersible's viewport, in the beam of powerful lights, he saw a world that seemed almost lunar in its barrenness. Pale mud stretched away in every direction. The water above was crystal clear, but utterly black beyond the reach of the lights. Yet even there, in the most extreme environment on Earth's surface, Cameron saw life. Small amphipods, shrimp-like creatures several inches long, appeared in front of the lights. A type of sea cucumber crept slowly across the mud. Later, analysis of the sediment samples he collected revealed bacteria thriving in the ooze, processing organic material that had drifted down from thousands of feet above. These creatures have evolved under pressures that would kill any surface-dwelling organism in Higgins. Their cells are filled with special molecules that prevent proteins from collapsing under the weight of all that water. Their bodies contain no air spaces that could be crushed. The Mariana Trench is not alone. The Pacific is lined with deep trenches where oceanic crust bends downward and begins its long descent into the mantle. The Tonga Trench near Fiji reaches depths of more than 35,000 feet. The Philippine Trench plunges to similar depths. The Peru-Chile Trench runs along the western coast of South America, marking where the Nazca Plate dives beneath the continent. Each of these trenches is a wound in the seafloor, a place where the solid surface of the planet opens to reveal the processes happening below. These trenches are also the places where the Pacific seafloor returns to the mantle from which it came. The rock that forms at mid-ocean ridges and spreads across the ocean floor eventually reaches a trench and begins to descend. As it sinks, it carries water trapped in its mineral structure down into the earth. That water plays a crucial role in generating the magma that feeds the Ring of Fire's volcanoes. In this way, the trenches and volcanoes are connected, two parts of the same cycle of creation and destruction that has been reshaping the Pacific for hundreds of millions of years. Between the mountains and the trenches lie the abyssal plains, vast flat regions that cover more of Earth's surface than any other environment. These plains lie 2 to 3 miles below the surface, beyond the reach of sunlight, blanketed in fine sediment that has been accumulating grain by grain for millions of years. The sediment consists of clay particles carried by currents, volcanic ash from distant eruptions, and the remains of microscopic organisms that once lived in the surface waters and drifted down after death. The abyssal plains seem featureless from a distance, but they too have their topography. Ancient lava flows from seafloor, spreading creates subtle ridges. Sediment builds up more thickly in some areas than others. Occasional boulders dropped by melting icebergs during ice ages lie scattered across the mud like glacial monuments in the deep. To descend into these depths is to travel through layers of the ocean, each with its own character and inhabitants. The surface waters are bright and warm, filled with microscopic plants that form the base of the ocean's food web. Below that lies the twilight zone, where some light penetrates but not enough for photosynthesis. Deeper still is the midnight zone, where darkness is absolute and strange fish with glowing lures and enormous eyes drift through the black water. Finally, there is the Hadal zone, named for Hades, the ancient Greek underworld. This zone exists only in the deepest trenches, in places where the seafloor drops below 20,000 feet. Each of these zones contains creatures exquisitely adapted to its conditions. In the twilight zone, fish have reflective scales that make them nearly invisible from below, blending with the dim light filtering down from above. In the midnight zone, bioluminescence becomes common. Organisms generate their own light through chemical reactions, using it to attract prey, find mates, or confuse predators. Some squid can create flashing displays of light along their bodies. Some jellyfish glow with soft blue light that pulses in the darkness. The topography of the Pacific floor shapes all of this life. Seamounts create upwelling currents that bring nutrients from the deep toward the surface, supporting rich ecosystems. Trenches provide habitats found nowhere else on Earth. The vast abyssal plains, though seemingly barren, host communities of organisms that process the slow rain of organic material from above, recycling nutrients and maintaining the chemical balance of the deep ocean. This hidden landscape also influences the ocean's currents. Water flowing across the sea floor must navigate around seamounts, through valleys, and over ridges. These features deflect currents, create turbulence, and mix water from different depths. The deep circulation of the Pacific, part of the global thermohaline current, often called the ocean conveyor belt, is shaped by the topography of the floor it flows across. Cold, dense water, formed in polar regions, sinks and flows along the bottom, eventually reaching the Pacific, where it spreads across the abyssal plains before slowly rising again in other parts of the ocean. When you look at the Pacific's surface, smooth and unchanging to the eye, it is easy to forget the drama beneath. But that hidden world is as real and as significant as any mountain range or valley on land. The trenches that plunge into darkness are as much a part of Earth's geography as the Himalayas or the Grand Canyon. The Pacific appears still when we look at its surface, but this stillness is an illusion. Beneath that glassy expanse, the ocean is always moving, flowing in great rivers that dwarf any current found on land. These rivers have no banks to contain them, no clear boundaries, to mark where they begin or end. They are made of water, moving through water, driven by wind, by the rotation of the earth, by differences in temperature and salinity, by the gentle but relentless push of the sun's heat and the moon's gravity. Together, these currents form circulation patterns so vast and so perfectly organized that they shape the climate of entire continents, guide the migrations of countless species, and connect every shore that touches the Pacific in a single fluid system. The largest of these circulation patterns are the Great Gyres, enormous spirals of moving water that turn slowly but ceaselessly in the northern and southern halves of the ocean. The North Pacific Gyre rotates clockwise, its currents forming a rough circle thousands of miles across. Water moves northward along the Asian coast, then eastward across the open ocean toward North America, then southward along the western coast of the Americas, and finally westward across the tropics to complete the circuit. This journey takes years, sometimes decades, as water makes its slow revolution around the gyre's enormous perimeter. The South Pacific Gyre turns in the opposite direction, counterclockwise, driven by the same forces, but responding to them differently because of the Earth's rotation and the different distribution of land in the southern hemisphere. Between these two great wheels of water lies the equatorial region, where currents flow predominantly from east to west, pushed by trade winds that have blown in the same direction for thousands of years. These equatorial currents are some of the fastest moving water in the ocean, rivers in the sea that carry more water than all the rivers on land combined. To understand what drives these currents, you must first imagine the surface of the ocean as a vast solar collector. Sunlight strikes the water and warms it, but that warming is not uniform. Near the equator, where the sun's rays hit most directly, the surface heats intensely. Near the poles, where sunlight arrives at a shallow angle and must pass through more atmosphere, the warming is much weaker. This temperature difference creates a kind of imbalance, a gradient that the ocean works constantly to even out. Warm water expands and becomes slightly less dense than cold water, so it tends to flow along the surface away from the equator, while cooler water from higher latitudes flows back toward the tropics to replace it. But the Earth is also spinning, rotating once every 24 hours. And this rotation deflects moving water in a phenomenon called the Coriolis effect. In the northern hemisphere, currents are deflected to the right of their direction of travel. In the southern hemisphere, they deflect to the left. This deflection is subtle, imperceptible to anything moving short distances, but over the vast scales of ocean basins, it becomes the dominant force organizing the currents. It is why the gyres spiral the way they do, why currents that start flowing north gradually curve eastward, and why the ocean's circulation forms these great rotating systems rather than simply flowing from equator to pole in straight lines. Wind plays an enormous role as well. The trade winds blowing westward across the tropical Pacific push surface water ahead of them, piling it up slightly on the western side of the ocean. The westerlies blowing eastward across the mid-latitudes do the same in reverse, creating currents that flow from west to east. Where winds blow consistently in the same direction for long periods, they drag the surface layer of the ocean along with them. That surface water then pulls on the water below it through friction, creating currents that extend downward hundreds of feet, sometimes deeper, each layer moving slightly slower and in a slightly different direction than the layer above. One of the most powerful currents in the Pacific is the Kuroshio Current, which flows northward along the coast of Japan. In Japanese, Kuroshio means black stream, a name given because the water in this current is deep blue, almost black. Its color a sign of the great depth from which it rises and the clarity of water that contains little suspended sediment. The Kuroshio is warm, carrying tropical heat northward into temperate latitudes, and it flows with remarkable speed, sometimes exceeding 4 miles per hour. This may not sound fast, but for an ocean current moving vast volumes of water, it is extraordinary. The Kuroshio moderates Japan's climate, keeping winters milder than they would otherwise be at those latitudes. Without this river of warm water flowing along its shores, Japan would be far colder, more like the northern regions of Canada or Russia that sit at similar distances from the equator. The current also supports rich fisheries, as the mixing of warm and cold waters creates conditions that nurture phytoplankton, which in turn feed the zooplankton and small fish that support larger species. For centuries, Japanese fishing villages have depended on the Kuroshio's bounty, and sailors have used its flow to travel more easily northward along the coast. On the eastern side of the Pacific, a very different current shapes the climate and ecology of South America. The Peru Current, also called the Humboldt Current, flows northward along the western coast of Chile and Peru, but unlike the Kuroshio, it is cold. This current originates in the Antarctic, drawing frigid water from the Southern Ocean and carrying it along the coast toward the equator. The cold water upwells near the shore, rising from the depths to replace surface water pushed offshore by winds. This upwelling brings nutrients from the deep ocean to the surface, creating some of the most productive marine ecosystems on Earth. The waters off Peru and Chile teem with life. Anchovies and sardines gather in enormous schools, their numbers so vast that they darken the water. Seabirds, by the millions, feed on these fish, diving and wheeling above the waves in a constant frenzy of hunting. Sea lions and fur seals patrol the coastline. Whales arrive to feed during certain seasons. The entire ecosystem depends on the Peru Current's delivery of nutrient-rich cold water to the surface, a process that has been operating for thousands of years and supports not only marine life, but also the human communities that fish these waters. But this system is not stable. Every few years, sometimes every decade, the normal pattern breaks down in a phenomenon called El Niño. During El Niño events, the trade winds that usually push surface water westward across the Pacific weaken or even reverse. Without that wind-driven push, the warm water that has piled up in the western Pacific flows back eastward, spreading across the ocean like a warm blanket. When this warm water reaches South America, it suppresses the upwelling of cold, nutrient-rich water. The anchovies and sardines, deprived of their food supply, either die or migrate away. The seabirds that depend on them starve. Fisheries collapse. The effects of El Niño extend far beyond the Pacific's eastern shore. The shift in ocean temperatures alters atmospheric circulation patterns worldwide. Regions that normally receive ample rainfall experience drought. Areas that are usually dry receive floods. The monsoons that billions of people depend on for agriculture can fail or arrive at the wrong time. Hurricanes form in unusual places or with unusual intensity. The entire global climate system responds to this change in the Pacific's circulation, demonstrating just how interconnected Earth's systems truly are. The opposite of El Niño is La Niña, when the trade winds blow even stronger than normal and push warm water even farther westward, intensifying the upwelling of cold water along the South American coast. During La Niña events, the climate effects are roughly opposite to those of El Niño, but still dramatic. Regions that flooded during El Niño may experience drought during La Niña. The Pacific's currents operate on cycles that we are only beginning to understand, oscillations that can last months or years and influence weather patterns across the entire planet. These shifts between El Niño and La Niña are part of a broader pattern called the El Niño Southern Oscillation, or ENSO, one of the most important sources of year-to-year climate variability on Earth. Scientists monitor the Pacific constantly, measuring sea surface temperatures, tracking wind patterns, and analyzing ocean currents to predict when these shifts will occur. Even with modern technology and sophisticated computer models, predictions remain uncertain. Beneath the surface currents that respond to wind and temperature, there exists an even deeper circulation, a slow conveyor belt of water that moves through the ocean at depths where sunlight never reaches. This deep circulation is driven not by wind, but by density differences created when cold, salty water forms in polar regions. When seawater freezes into ice, the salt is left behind in the remaining liquid, making it even saltier and therefore denser. This dense water sinks to the ocean floor and begins a journey that can last centuries. In the North Atlantic, this process creates deep water that flows southward toward Antarctica, then eastward around the Southern Ocean, and finally northward into the Pacific. When that deep water finally reaches the North Pacific, it has been traveling for more than 1,000 years, carrying with it dissolved oxygen and nutrients from its origin point. Eventually, this deep water rises back toward the surface through a process called upwelling, mixing with warmer surface waters and beginning the cycle again. The entire global circulation takes about 1,000 years to complete, a conveyor belt moving water and heat and dissolved gases around the planet in the slowest of rhythms. The Pacific plays a crucial role in this global circulation. Because it is the largest ocean, it holds the most water, and changes in Pacific circulation can affect the entire global system. The deep Pacific stores enormous amounts of carbon dioxide absorbed from the atmosphere centuries ago. It holds heat that will eventually return to the surface and influence future climates. It is a reservoir of memory, carrying information about past conditions forward through time in the chemistry and temperature of its deep waters. Marine life has learned to follow these currents, using them as highways across the ocean. Sea turtles ride the North Pacific Gyre in a great circle that takes years to complete, timing their reproduction to coincide with their arrival at specific beaches. Salmon leave their natal rivers and enter the ocean, where they travel thousands of miles guided by currents and their own mysterious sense of navigation, before returning years later to the exact streams where they were born. Whales migrate along current boundaries where different water masses meet and nutrients concentrate, following patterns their species has followed for millions of years. Even creatures too small to see with the naked eye ride the currents. The larvae of coral, fish, and invertebrates drift as plankton, carried by currents away from where they were born. Some will settle successfully in new locations, founding new populations and maintaining genetic connections between distant reefs and shores. Others will be carried out into the open ocean, where no suitable habitat exists, but even these play a role, becoming food for filter feeders and transferring energy from coastal waters to the deep sea. The currents are life's distributors, spreading organisms across the ocean, connecting populations separated by thousands of miles of water. When you swim in the Pacific, you enter these currents and become part of their flow. You may not feel them strongly, may not notice any particular direction of movement, but they are there. Gentle pressures in the water, subtle tugs and pushes. If you were to release a floating object and watch it over hours or days, you would see it drift, following paths traced by water that knows where it is going, even if you do not. These paths are invisible to the eye, but as real as any road on land, and they carry infinitely more traffic, more life, more energy than any highway humanity has ever built. The Pacific Ocean is not merely water, it is alive. Every drop teems with microscopic organisms. Every cubic meter holds creatures in numbers beyond counting. From the smallest bacteria to the largest animals ever to exist on Earth, from creatures that drift passively with the currents to predators that hunt with extraordinary intelligence, the Pacific contains more life, more diversity, more biological abundance than any other ocean on the planet. It is a living tapestry woven from millions of species, each adapted to its particular niche, each playing its role in maintaining the intricate balance that allows the ocean to function as a single, vast ecosystem. To understand the Pacific's abundance, you must begin at the foundation, with organisms so small that millions could fit in a teaspoon of seawater. Phytoplankton, microscopic plants that drift in the surface waters, form the base of nearly every food chain in the ocean. These tiny organisms, most of them single-celled, contain chlorophyll and perform photosynthesis just like trees and grasses on land. They absorb carbon dioxide from the water and use sunlight to convert it into organic matter, releasing oxygen as a byproduct. It is estimated that phytoplankton produce more than half of the oxygen in Earth's atmosphere, more than all the forests and grasslands combined. The Pacific's phytoplankton exist in countless varieties. Diatoms, with intricate glass shells, dinoflagellates that can produce bioluminescent light, cyanobacteria that have been performing photosynthesis for billions of years. Each species has its preferred conditions, its optimal temperature and nutrient levels. And as currents mix the water and seasons change, different species bloom and fade in succession. When conditions are right, phytoplankton can multiply so rapidly that they color the water, turning it milky green or rusty red in blooms that can be seen from space. These blooms attract the next level of the food chain. Zooplankton, tiny animals that drift with the currents, feed on phytoplankton. Many zooplankton are the larval stages of creatures that will grow much larger. baby crabs, and fish and jellyfish, spending their early days as part of the plankton before settling down or developing into their adult forms. Others remain small throughout their lives, like copepods, shrimp-like creatures no bigger than a grain of rice that exist in such astronomical numbers that they may be the most abundant animals on Earth. A single cubic meter of Pacific water can contain thousands of copepods, all grazing on phytoplankton, all themselves serving as food for larger creatures. Small fish gather to feed on this bounty. Anchovies and sardines form schools so vast that they stretch for miles, their silver bodies flashing in synchronized waves as they turn and dive through clouds of plankton. These schooling fish are some of the most important creatures in the Pacific, serving as the primary food source for larger predators. Tuna hunt them. Dolphins and seals chase them. Seabirds dive through the surface to catch them. Whales engulf them by the ton. Without these small fish converting plankton into protein that larger animals can use, the ocean's great predators could not exist. The Pacific contains more species of fish than any other ocean. Scientists have cataloged tens of thousands of species, and new ones are discovered regularly. Some are tiny gobies, no longer than your thumbnail, living in the shallow waters of coral reefs. Others are massive groupers weighing hundreds of pounds, lurking in caves and crevices. There are flying fish that leap from the water and glide on enlarged fins, escaping predators by temporarily leaving their element. There are sailfish and marlin that swim faster than most boats can travel, their streamlined bodies and powerful tails capable of bursts exceeding 60 miles per hour. In the open ocean, tuna roam in schools, following currents and temperature boundaries where prey concentrates. Bluefin tuna, the largest species, can grow to more than 1,000 pounds and swim across entire ocean basins, migrating from breeding grounds near Japan to feeding areas off California and back again. Their bodies maintain temperatures higher than the surrounding water through specialized circulation systems, allowing them to hunt in cold waters where other fish become sluggish. They are warm-blooded in a sense, an adaptation so rare in fish that it speaks to the evolutionary pressures of life in the open ocean, where the fastest and most efficient hunters survive. Sharks patrol the Pacific in their ancient role as apex predators. Great white sharks cruise the coasts, hunting seals and sea lions with patience and explosive bursts of speed. Hammerhead sharks, with their bizarre T-shaped heads covered in electrical sensors, sweep the sea floor, detecting the bioelectric fields of buried rays and fish. Tiger sharks, less selective in their diet, consume everything from sea turtles to seabirds to carrion drifting down from the surface. And in the deep ocean, where darkness is absolute, bizarre sharks with glowing bodies and long teeth hunt in the eternal night, species so rarely seen that most of what we know about them comes from occasional specimens caught by research vessels. But perhaps no creatures define the Pacific's abundance more than the coral reefs. These structures, built by tiny animals no bigger than your fingernail, form the most biodiverse ecosystems in the ocean, marine equivalents of rainforests where life concentrates in extraordinary density. The Great Barrier Reef, stretching along Australia's northeastern coast, extends partly into Pacific waters, though most of it lies in the Coral Sea. But the true heart of Pacific coral diversity lies farther north and west in a region called the Coral Triangle. The Coral Triangle, encompassing waters around Indonesia, the Philippines, and Papua New Guinea, contains the highest diversity of marine life on Earth. More than 600 species of reef-building corals exist here, compared to fewer than 100 in the Caribbean. More than 3,000 species of fish, 6 of the world's 7 sea turtle species. The region is a living library of evolutionary experimentation, a place where every possible body shape, color pattern, feeding strategy, and reproductive method seems to have been tried and perfected over millions of years. Walk through a coral reef, or rather, swim slowly above it, and you witness a spectacle that overwhelms the senses. The corals themselves come in every imaginable form. Brain corals with surfaces that look exactly like the folds of a human brain. Staghorn corals branching like antlers. Table corals spreading horizontally to catch more sunlight. Soft corals that sway with the currents, their bodies flexible rather than rigid. Each coral is actually a colony of individual polyps, tiny animals related to jellyfish and anemones, working together to build a shared calcium carbonate skeleton that provides protection and structure. The colors are impossible to describe fully. Electric blue parrotfish graze on algae, their beaks strong enough to bite chunks of coral, which they grind up and excrete as sand. Schools of yellow tangs flow like liquid gold over the reef. Clownfish, vivid orange with white stripes, dart among the tentacles of sea anemones, protected by a coating of mucus that prevents the anemone's stinging cells from firing. Lionfish, beautiful and venomous, extend their elaborate fins as they hover in the water, their bodies striped in red and white, their movements slow and deliberate because they have no predators and no need to hurry. Eels peer from crevices, their long bodies hidden except for heads that sway back and forth, mouths occasionally opening to reveal rows of teeth. Octopuses, perhaps the most intelligent invertebrates on Earth, change color and texture in an instant, transforming from brown and bumpy to match rock, then to white and smooth to match sand, then to a pattern of stripes and spots when they decide to reveal themselves. They hunt at night, squeezing their boneless bodies through impossibly small gaps, solving problems with brains distributed partly through their 8 arms. Manta rays glide over the reef like underwater birds, their wingspans reaching 15 feet or more, their mouths open as they filter plankton from the water. Sea turtles paddle slowly past, ancient and serene, surfacing occasionally to breathe before diving back down to graze on seagrass or rest on sandy patches between coral formations. Some of these turtles are older than the humans watching them, having roamed the Pacific for 50 years or more, returning every few years to the same beaches where they hatched to lay their own eggs in the sand. The reef is noisy. Parrotfish scraping coral, shrimp snapping their claws with sounds like breaking twigs, fish communicating with grunts and clicks. The collective sound of the reef carries through the water, audible from a distance, a biological symphony that plays continuously as long as the reef is healthy. Scientists have discovered that larval fish use these sounds to find reefs in the open ocean, following the noise home to suitable habitat where they can settle and complete their development. At night, the reef transforms completely. Many day-active fish hide in crevices to sleep. Nocturnal predators emerge. Coral polyps extend their tentacles to feed on plankton drifting past. Bioluminescent creatures begin to glow. Flashlight fish swim with pockets of luminous bacteria under their eyes, blinking the lights on and off to confuse predators or communicate with others of their kind. The reef becomes a constellation of living stars, points of blue-green light appearing and disappearing in the darkness. The Pacific reefs support human communities as well as marine life. Millions of people depend on reef fisheries for protein. Coastal communities derive their primary income from the ocean, going out each day in small boats to catch fish and octopus and lobster. Tourism brings visitors from around the world to snorkel and dive, to witness the reef's beauty firsthand, generating billions of dollars in revenue that supports island economies. The reefs also protect coastlines from storm surge and erosion, their complex structures breaking waves and reducing the energy that reaches the shore. Beyond the reefs, in the open ocean, other giants roam. Whales, the largest creatures ever to exist on Earth, migrate across the Pacific in patterns that have remained unchanged for millions of years. Blue whales, growing longer than 100 feet and weighing more than 200 tons, glide through the water with a grace that seems impossible for something so enormous. They feed on tiny krill, filtering thousands of pounds of the shrimp-like creatures from the water each day. A blue whale's heart weighs as much as a small car. Its blood vessels are wide enough that a human child could crawl through them. When it surfaces to breathe, its spout of exhaled air shoots 30 feet into the sky, visible for miles. Humpback whales sing in the Pacific, their complex songs carrying for dozens of miles through the water. Each population has its own dialect, its own variations on the themes that all humpbacks share. The songs change slowly over time, new phrases appearing and spreading through the population as individuals learn from each other and add their own improvisations. Scientists who study these songs believe they serve multiple purposes: attracting mates, establishing territory, perhaps simply expressing something we might recognize as joy or sociability, if we encountered it in creatures more like ourselves. Gray whales make one of the longest migrations in the animal kingdom, traveling from feeding grounds in the Arctic to breeding lagoons in Mexico and back again each year, a round trip of more than 12,000 miles. They swim close to shore for much of this journey, following the coastline, and people gather on cliffs and beaches to watch them pass. These great gray shapes rolling through the swells, occasionally breaching entirely clear of the water and crashing back down in explosions of white spray. Sperm whales dive deeper than any other marine mammal, descending more than 7,000 feet to hunt giant squid in the darkness. They can hold their breath for more than an hour, their bodies adapted to pressures that would collapse human lungs. In the deep, they use echolocation to navigate and hunt, producing the loudest sounds made by any animal. Clicks so powerful they can be felt as vibrations even through the hull of a submarine. These clicks are thought to stun prey, perhaps even killing squid, with focused blasts of sound before the whale closes in to feed. Dolphins swim in pods ranging from a handful of individuals to superpods numbering in the thousands. They are intensely social, cooperating to hunt, to protect each other from sharks, to care for injured members of their group. They communicate with a language of clicks, whistles, and body postures that scientists are only beginning to decode. Each dolphin has a signature whistle that serves as its name, and others use that whistle to call to specific individuals, demonstrating a level of abstract communication rare in the animal kingdom. In the deep ocean, where sunlight never reaches, bizarre creatures have evolved in forms that seem alien. Anglerfish dangle bioluminescent lures in front of their mouths, attracting prey close enough to snap up in jaws, lined with teeth like needles. Gulper eels have mouths larger than their entire bodies, capable of swallowing prey even larger than themselves. Vampire squid, despite their ominous name, are gentle creatures that feed on marine snow, the continuous rain of organic particles drifting down from surface waters. They have the largest eyes relative to body size of any animal on Earth. Dinner plate-sized organs that gather every photon of light in the near-total darkness where they live. Jellyfish pulse through the water in every ocean layer, from the surface down to the Hadal depths. Some are tiny and transparent, barely visible. Others, like the lion's mane jellyfish, grow tentacles more than 100 feet long, trailing behind a bell several feet across. The sting of some jellyfish is painful but harmless to humans. Others, like the box jellyfish found in Pacific waters near Australia and Southeast Asia, carry venom potent enough to kill an adult within minutes. These creatures have been drifting through the oceans for more than 500 million years, predating most other complex life forms, and they continue to thrive in their ancient simplicity. The abundance of the Pacific is not evenly distributed. In some areas, particularly the central gyres, where nutrients are scarce and currents circulate slowly, life is sparse. These regions are sometimes called ocean deserts, though even there, phytoplankton exist and support small populations of other organisms. But where conditions are right, where nutrients upwell from the deep, or where currents converge, life explodes in profusion. These productive zones support fisheries that feed hundreds of millions of people. They attract megafauna from across the ocean. They are the oases of the sea, and around them, entire economies and cultures have developed. There are places in the Pacific where sunlight has never reached, where the darkness is so complete and so eternal that the very concept of light becomes meaningless. Descend far enough beneath the surface, past the sunlit zone where phytoplankton drift, past the twilight zone where the last dim rays fade into shadow, and you enter a realm that seems incompatible with life. The pressure here would crush a human body instantly. The temperature hovers just above freezing. No plant can grow in this darkness. No photosynthesis can occur. And yet, impossibly, abundantly, life thrives here. Strange creatures have evolved in forms that seem borrowed from nightmares and dreams, adapted to conditions so extreme that discovering them has forced scientists to reconsider what life requires, what it can endure, and where else in the universe it might exist. This is the Hadal Zone, named after Hades, the ancient Greek underworld, a region that exists only in the deepest trenches where the sea floor plunges below 20,000 feet. To reach these depths is to descend more than 3 miles below the ocean surface into a world that fewer humans have visited than have walked on the moon. The journey down takes hours, even in the fastest submersibles. As you descend, you pass through layers of decreasing light and increasing pressure, watching the blue water darken to purple, then to black, until finally, even the most sensitive instruments detect nothing but absolute darkness. The pressure at these depths defies easy comprehension. At the bottom of the Mariana Trench, in the Challenger Deep, nearly 7 miles down, the pressure exceeds 16,000 pounds per square inch, more than 1,000 times the atmospheric pressure at sea level. This is equivalent to having 50 jumbo jets stacked on top of every square inch of your body. Any airspace, any gas bubble, any hollow structure would collapse instantly. A styrofoam cup sent down in a sample cage returns compressed to the size of a thimble, its structure crushed by the weight of all that water pressing inward from every direction. Yet life has found ways to exist under these conditions. The creatures of the Huddall zone have bodies with no air spaces, no swim bladders, no lungs filled with compressible gas. Their cells are filled with special molecules that prevent proteins from collapsing under pressure. Their bodies contain high concentrations of a compound called trimethylamine oxide, or TMAO, which counteracts the effects of pressure on cellular structures. The deeper they live, the more TMAO they produce, adjusting their internal chemistry to match the demands of their environment. One of the most remarkable fish ever discovered lives at depths greater than 26,000 feet in the Mariana Trench. The Mariana snailfish, discovered only recently, holds the record for the deepest living fish ever observed. It is small, translucent, and almost ghostly in appearance, with a body that seems too delicate to exist in such a harsh environment. Its bones are thin and flexible rather than rigid. Its body is mostly water and gelatin, offering little resistance to the crushing pressure. It has no scales, and its skin is nearly transparent, revealing the organs within. The snailfish feeds on tiny amphipods, shrimp-like crustaceans that themselves are remarkable for thriving at such depths. These amphipods are actually quite large compared to their shallow water relatives, some growing several inches long, and they scavenge organic material that drifts down from above or hunt even smaller creatures in the sediment. When researchers sent baited cameras to the bottom of the trench, amphipods swarmed to the bait in such numbers that they completely obscured the camera's view within minutes, their pale bodies piling on top of each other in a feeding frenzy that demonstrated the presence of a surprisingly robust ecosystem, even in this most extreme environment. The creatures of the deep have lost many features that surface-dwelling animals take for granted. Eyes, so crucial for navigating a world of light, become useless in absolute darkness. Many deep-sea fish have either reduced eyes or no eyes at all. Their optic nerves atrophied over millions of years of evolution in an environment where sight provides no advantage. Instead, they navigate by feeling pressure waves in the water, detecting the movement of other creatures through sensitive organs along their bodies called lateral lines. Some can sense the faint electrical fields generated by muscle contractions in prey, allowing them to hunt in darkness with eerie precision. Other creatures have taken the opposite approach, developing eyes so large and sensitive that they can detect the faintest bioluminescent glow. The barrel-eye fish has tubular eyes that point upward, perpetually scanning the water above for the silhouettes of prey backlit by distant bioluminescence. These eyes are protected by a transparent dome that covers the top of the fish's head, giving it one of the most bizarre appearances of any creature on Earth. The eyes can rotate within this dome, allowing the fish to look forward when it needs to bring food to its mouth, then back upward to resume its eternal watch. Bioluminescence becomes crucial in the deep ocean. In a world without sunlight, organisms create their own light through chemical reactions. More than 90% of creatures living in the deep ocean can produce light in some form, either through their own biochemistry or through symbiotic relationships with bioluminescent bacteria. The light they produce is usually blue or green, colors that travel farthest through water, though some species produce red light, which most deep-sea creatures cannot see, effectively giving them a private spotlight that illuminates prey without revealing their own presence. The anglerfish uses bioluminescence as a lure, dangling a glowing appendage in front of its enormous mouth to attract curious prey close enough to strike. Female anglerfish can grow to impressive sizes, their bodies round and dark, their mouths filled with long, needle-like teeth that point inward, making escape impossible once something has been caught. The males, bizarrely, are tiny in comparison, sometimes just inches long. When a male finds a female, he bites into her body and fuses with her permanently, his circulatory system merging with hers. He becomes essentially a parasite, or perhaps better understood as a permanent sperm donor, receiving nutrients from her bloodstream while providing sperm when needed. In the vast darkness of the deep ocean, finding a mate is so difficult that when males do encounter females, they commit completely, surrendering their independence for the security of a permanent partnership. The gulper eel, also called the pelican eel, has evolved a mouth so large that it seems to be mostly mouth with a small body attached. The mouth can unhinge and expand to swallow prey larger than the eel's entire body. This adaptation makes sense in an environment where food is scarce and unpredictable. When something edible appears, you must be prepared to consume it no matter the size, because you may not encounter another meal for weeks or months. The gulper eel's stomach can expand to accommodate these enormous meals, stretching like a balloon, and then the fish can live off that single feeding for extended periods while digesting slowly in the darkness. Despite their fearsome appearances, many deep-sea creatures are quite small and fragile. They expend minimal energy, moving slowly or not at all, waiting patiently for food to drift within reach. Their metabolisms operate at a fraction of the rate of surface-dwelling fish. They grow slowly, reproduce infrequently, and live long lives in their cold, dark world. Some deep-sea fish may live for decades or even centuries, their bodies aging so slowly in the near-freezing water that time itself seems to move differently than it does in the warm, sunlit surface. The vampire squid, despite its ominous name, is not a predator, but a gentle scavenger. It feeds on marine snow, the constant drift of organic particles falling from the surface toward the seafloor. Dead plankton, fecal matter from surface-dwelling creatures, fragments of jellyfish, and other gelatinous animals. All of this material sinks slowly through the water column, and the vampire squid catches it with specialized filaments that extend from its body. It has the largest eyes relative to body size of any animal on Earth, each eye the size of an orange on a body only about a foot long. These enormous eyes gather every available photon of light, allowing the squid to see bioluminescent flashes in the darkness and to navigate through a world where most creatures are effectively blind. The deep ocean is not silent. While light does not penetrate to these depths, sound travels remarkably well through water, better than it does through air. The ocean's depths echo with clicks, buzzes, and strange sounds that scientists are still working to identify. Some sounds come from marine mammals far above, their vocalizations traveling miles through the water. Others are produced by the creatures of the deep themselves, communicating or echolocating in ways we are only beginning to understand. And some sounds remain mysteries, like the famous bloop detected in 1997, an ultra-low frequency sound powerful enough to be picked up by sensors thousands of miles apart. Its source never conclusively identified. Food is the primary challenge of deep-sea life. With no photosynthesis possible, all energy must ultimately come from the surface. Dead organisms sink, creating a rain of organic material that sustains the deep-sea ecosystem. But this rain is sparse and unpredictable. A whale carcass falling to the seafloor becomes an oasis, supporting specialized communities for years as scavengers feed on the bones and flesh. Sleeper sharks, enormous and slow-moving, patrol the depths, looking for carrion or hunting the occasional fish. Hagfish, primitive eel-like creatures that have remained essentially unchanged for hundreds of millions of years, congregate around any source of food, burrowing into dead animals and consuming them from the inside out. But in certain places, deep-sea life has discovered a way to bypass the surface entirely, to harvest energy directly from the Earth itself. At hydrothermal vents, where seawater seeps into cracks in the seafloor and encounters magma chambers below, superheated water shoots back up into the ocean, laden with dissolved minerals and chemicals. These vents, called black smokers because of the dark plumes they produce, create conditions that seem utterly hostile to life. The water temperature can exceed 700 degrees Fahrenheit, hot enough to melt lead. The chemical mixture includes hydrogen sulfide, which is toxic to most life forms. Yet around these vents, ecosystems flourish in densities that rival coral reefs. Giant tube worms, some growing more than 6 feet long, anchor themselves near the vents and extend their red plumes into the water to absorb hydrogen sulfide and oxygen. Inside their bodies, they harbor billions of chemosynthetic bacteria that use the hydrogen sulfide as an energy source, much like plants use sunlight. The bacteria convert this chemical energy into organic compounds, which the tube worms absorb as food. The worms have no mouths, no digestive systems. They are entirely dependent on their bacterial partners in one of the most remarkable symbiotic relationships known to science. Around the tube worms cluster other organisms. Crabs scuttle across the rocks, their white bodies lacking pigment because color serves no purpose in darkness. These vent crabs are covered with bacteria-laden hairs that may also harvest chemical energy. Shrimp swarm in the plumes, their backs equipped with primitive light sensors that detect the faint infrared glow of the superheated water, helping them stay close enough to benefit from the vent's chemistry without swimming so close that they cook. Clams and mussels filter bacteria from the water, their bodies also hosting internal bacterial colonies. These vent ecosystems are islands of abundance in the desert of the deep sea floor. They exist completely independently of the sun, powered instead by the Earth's internal heat. The discovery of these communities in the 1970s revolutionized biology, proving that life does not require photosynthesis, that alternative energy sources can support complex ecosystems. This discovery has profound implications for the search for life elsewhere in the universe. If life can thrive in Earth's deep ocean without sunlight, perhaps similar ecosystems exist in the subsurface oceans of Europa or Enceladus, moons of Jupiter and Saturn, where liquid water exists beneath shells of ice, warmed by tidal heating rather than stellar radiation. The vents themselves are temporary. They form along mid-ocean ridges where new oceanic crust is being created, and they cease flowing when volcanic activity shifts elsewhere. A vent might remain active for decades or centuries, but eventually it cools and dies. When that happens, the communities surrounding it must disperse, their larvae drifting with deep ocean currents until they encounter another active vent where they can settle. This means that vent species must be capable of long-distance dispersal, and their larvae must be able to survive weeks or months drifting through the darkness, sustained by internal energy stores, waiting for chemical cues that signal the presence of a new vent. Scientists study these creatures with awe and puzzlement, trying to understand how they navigate, how they find new vents, how their populations remain genetically connected across vast distances. The deep ocean remains one of the least explored regions on Earth. We have better maps of the surface of Mars than we do of most of the deep Pacific seafloor. Each expedition brings back new species, new behaviors, new mysteries. It is estimated that millions of species remain undiscovered in the deep ocean, creatures that have never been seen by human eyes, that live and die in darkness without ever being known to exist. Beneath the waves, where sunlight fades to memory and pressure builds with every meter of descent, the Pacific floor holds treasures older than human civilization. Scattered across the abyssal plains, resting in darkness so complete it seems almost solid, lie billions upon billions of mineral nodules. Small, dark, and humble in appearance, they resemble potatoes made of stone, each one roughly the size of a fist or smaller, clustered together like a garden that has been growing in silence for epochs beyond counting. These nodules are not placed there by chance, nor are they the remains of some ancient catastrophe. They grow slowly, imperceptibly, molecule by molecule. They accumulate metals from the seawater that drifts past them in the eternal cold. Manganese and iron form their cores and outer layers, darkening them to near black. But within and around these stones lie other elements, rarer and more precious. Cobalt, which powers our batteries and colors our glass. Nickel, strong and resistant to corrosion. Copper, the ancient metal of wires and tools. And scattered throughout, in concentrations that surprise geologists, are the rare earth elements: neodymium for magnets, yttrium for lasers and superconductors, cerium, lanthanum, and others whose names sound like incantations from another world. These elements, so crucial to modern technology, from smartphones to wind turbines to medical imaging devices, accumulate in the darkness of the Pacific, settling into nodules that rest undisturbed on plains of soft sediment thousands of meters below the surface. The formation of these nodules is a process that demands patience on a geological scale. They grow at rates almost too slow to comprehend, adding perhaps a few millimeters every million years. Imagine a stone taking 10 million years to grow from the size of a pebble to the size of a potato. The nodules you might find on the Pacific floor today began forming during the age of the dinosaurs, or even earlier, accumulating metal atoms one by one as ocean currents carried dissolved minerals past them in the deep. The metals come from multiple sources. Some dissolve from volcanic rocks on the seafloor, leached out by seawater over millennia. Others arrive from above, carried down in the form of dead organisms, tiny particles of organic matter that drift like snow through the water column, bringing with them trace metals absorbed during life. Hydrothermal vents, those smoking chimneys scattered along mid-ocean ridges, also contribute, exhaling mineral-rich water that eventually settles and precipitates across vast distances. The nodules are collectors, patient and indiscriminate, gathering whatever the ocean offers. Some estimates suggest there are trillions of tons of these nodules resting on the Pacific floor, enough to supply humanity's metal needs for centuries. But the nodules are not the only mineral wealth hidden in the deep. Along the mid-ocean ridges, where the Earth's crust splits open and new seafloor is born, hydrothermal vents release not just heat and chemicals, but metals in concentrated forms. These vents, discovered only in the late 1970s, are underwater chimneys built from minerals that precipitate out of the superheated water as it meets the cold ocean. The structures they create can tower several stories high, black and rust-colored, encrusted with sulfides of copper, zinc, gold, and silver. Around these vents, the metals accumulate in mounds and crusts, concentrated in ways rarely seen elsewhere on Earth. The deposits form quickly by geological standards, building up over thousands rather than millions of years, fed by the continuous flow of mineral-laden water from deep within the planet. Prospectors have identified fields of these deposits scattered along the Pacific Ring of Fire and the East Pacific Rise, each site a potential mine, each location rich enough to warrant interest from industries hungry for raw materials. Beneath the continental shelves, where the Pacific laps against the edges of Asia, the Americas, and Oceania, lie other treasures entirely. Oil and natural gas, the compressed and transformed remains of ancient marine organisms, rest in pockets within sedimentary rock formations. These fossil fuels, created over millions of years from the bodies of plankton and algae that once drifted in sunlit surface waters, now lie trapped beneath layers of stone and sand. Drilling platforms dot the shallow Pacific, extracting these resources to power the modern world, a trade of ancient sunlight stored in carbon chains for the energy needs of today. The scale of these resources is staggering. The Pacific's seafloor holds enough minerals to transform global supply chains, enough metals to build infrastructure for billions of people, enough rare earth elements to power the transition to renewable energy technologies. It is a vault of geological wealth, quietly waiting in the darkness, accumulated over timescales that dwarf human history. And yet, this abundance brings with it questions that are anything but simple. And so we must ask ourselves, what kind of relationship do we want with this hidden world? Do we see it primarily as a storehouse of resources, waiting to be unlocked and utilized? Or do we recognize it as something more, an ecosystem of intrinsic value, a library of Earth's history, a frontier that might teach us things we cannot yet imagine if we approach it with patience and respect? Perhaps the answer lies somewhere between these extremes, in a careful, slow approach that prioritizes understanding before extraction, that establishes protections before permits, that recognizes both the value of resources and the irreplaceable nature of ecosystems we are only beginning to comprehend. The Pacific Ocean does not simply exist beneath the sky, it shapes it. Every day, as sunlight pours down onto the vast expanse of water, the ocean absorbs heat with a capacity that dwarfs any land surface. Water, molecule by molecule, stores thermal energy far more efficiently than rock or soil or air. The Pacific, covering nearly a third of the planet's surface, acts as an enormous solar collector, gathering warmth during the day, across seasons, and over years, holding it in its depths like a memory that can last for centuries. This stored heat does not simply sit there, static and unchanging. It moves. Currents carry warm water from the tropics toward the poles, and cold water from polar regions toward the equator, creating a global conveyor belt of temperature redistribution. The Pacific is constantly balancing Earth's energy budget, taking excess heat from regions where the sun beats down most intensely and delivering it to places where sunlight arrives at gentler angles. Without this ocean thermostat, the tropics would be unbearably hot, and the poles would be even more frozen than they already are. The temperature differences between these regions would be so extreme that life as we know it could not exist across such a wide range of latitudes. The Pacific's surface layer, warmed by the sun, can reach temperatures exceeding 30 degrees Celsius in the tropics, creating vast pools of heat that hold more energy than all the world's power plants could generate in years. This warm water fuels the atmosphere above it, evaporating into water vapor that rises, carrying heat upward and feeding the clouds that drift across the sky. As the vapor rises and cools, it releases that heat into the upper atmosphere, driving wind patterns and weather systems across thousands of kilometers. But beneath this warm surface layer lies something even more remarkable. The deeper waters of the Pacific, sheltered from direct sunlight, remain cold, hovering just above freezing even in tropical latitudes. This temperature stratification creates a stable structure where warm water floats atop cold, separated by a transition zone called the thermocline. In some places, this boundary is sharp enough that you could swim from bathwater warmth into shocking cold within a few meters of descent. This layering is not merely a curiosity. It fundamentally controls how the ocean absorbs, stores, and releases heat over time. When surface waters cool, perhaps during a storm or in winter months, they can sink, carrying their heat signature downward. This process, called convection, allows the ocean to store heat at depth, removing it from immediate contact with the atmosphere. Years, or even decades later, when ocean circulation brings those deeper waters back to the surface, they can release that stored heat, influencing weather patterns long after the original warming occurred. The Pacific, in this way, has a memory, a thermal inertia that smooths out temperature extremes and influences climate on timescales far longer than any single season. But the Pacific does more than store and move heat. It also absorbs carbon dioxide from the atmosphere, playing a crucial role in regulating the greenhouse gases that control Earth's temperature. When carbon dioxide from the air touches the ocean surface, it dissolves into the seawater, reacting with water molecules to form carbonic acid. This process is invisible, silent, and constant, happening across every square meter of the Pacific's surface, every moment of every day. The ocean acts as a chemical sponge, soaking up roughly a quarter of all the carbon dioxide that human activities release into the atmosphere. Without this service, the atmosphere would contain far more carbon dioxide than it currently does, and the warming of the planet would be accelerating even faster than we observe. The Pacific, simply by existing as a vast body of water, is slowing the pace of climate change, giving humanity more time to respond to the consequences of burning fossil fuels. It is a gift we rarely acknowledge, this quiet absorption of our excess carbon. But it is also a process that comes with a cost. As carbon dioxide dissolves into seawater and forms carbonic acid, the ocean's chemistry slowly changes. The pH of the water decreases, making it more acidic. This process, called ocean acidification, happens gradually, imperceptibly to the casual observer, but with profound consequences for marine life. Many organisms build their shells and skeletons from calcium carbonate, a mineral that dissolves more easily in acidic conditions. Corals, mollusks, certain types of plankton, all of these creatures face a more difficult chemical environment as the ocean's pH drops. The change is not dramatic from year to year. Corals do not suddenly crumble, and clams do not instantly lose their shells. But over decades, the accumulated effect becomes measurable. Coral growth slows. Shell formation requires more energy. The larval stages of many marine animals, which are particularly sensitive to pH changes, face higher mortality rates. Scientists studying the waters off the Pacific coast have documented these shifts, watching as the ocean's chemistry drifts away from the conditions that have prevailed for millions of years, changing within a single human lifetime. This acidification is not evenly distributed across the Pacific. Upwelling zones, where deep, cold water rises to the surface, bring water that is already naturally more acidic and lower in oxygen. These regions, particularly along the coasts of North and South America, experience more pronounced acidification, creating challenging conditions for the rich ecosystems that depend on these productive waters. Fisheries notice it in the form of smaller shellfish harvests, Marine biologists see it in laboratory studies where organisms struggle to build shells in water samples taken from these zones. Yet even as the ocean absorbs our carbon and becomes more acidic, it continues to regulate the planet's temperature through other mechanisms. The Pacific's temperature patterns influence weather systems, not just locally, but across continents. The warm waters of the western tropical Pacific, where sea surface temperatures remain consistently high, act as an enormous heat engine for the atmosphere. Air above this warm water rises vigorously, creating low pressure at the surface that draws in moisture-laden winds from surrounding regions. This rising air, laden with water vapor, cools as it ascends, and the vapor condenses into towering clouds that stretch from the ocean surface to the top of the troposphere. The condensation releases heat, further fueling the upward motion of air, creating a powerful cycle that drives some of the most dramatic weather patterns on Earth. Monsoons, those seasonal reversals of wind and rain that dominate much of South and Southeast Asia, are powered by temperature contrasts between the Pacific Ocean and the continental land masses. When the ocean is warmer than the land, moist air flows inland, bringing rains that sustain billions of people. Typhoons in the western Pacific and hurricanes in the eastern Pacific are born from this same process. These massive rotating storms form over warm tropical waters where the ocean surface exceeds about 26 degrees Celsius. The heat and moisture from the ocean fuel their development, feeding them energy as water vapor evaporates from the surface, rises, and condenses into clouds. The warmer the ocean, the more energy is available, and the more intense these storms can become. As the Pacific warms due to climate change, scientists observe trends towards stronger storms, hurricanes that intensify more rapidly, and typhoons that carry more rainfall, capable of devastating coastal communities. The Pacific's influence extends far beyond the tropics. High above the ocean, in the upper atmosphere, flows the jet stream, a ribbon of fast-moving air that circles the planet at mid-latitudes. The position and strength of the jet stream are influenced by temperature contrasts between different regions, and the Pacific plays a crucial role in setting up these contrasts. When the tropical Pacific is unusually warm, as during El Niño events, the jet stream shifts, changing storm tracks across North America. Winters become wetter in the southern United States, drier in the Pacific Northwest. The effects ripple across continents, influencing rainfall patterns from California to Australia. During La Niña, when the tropical Pacific is cooler than average, the jet stream shifts again, bringing different patterns. The western United States tends to be drier, the Pacific Northwest wetter. Hurricanes in the Atlantic may become more numerous. These oscillations between El Niño and La Niña, driven by interactions between the ocean and atmosphere in the Pacific, demonstrate how intimately connected the ocean is to global weather patterns. A change in sea surface temperature of just a few degrees in one part of the Pacific can trigger droughts in Africa, floods in South America, and unusual snowfall in regions that rarely see winter storms. These patterns are not new. They have been operating for millennia, shaping the climate that civilizations rose and fell within. But scientists studying ocean sediments have found records of how these patterns have changed over even longer timescales. By drilling into the seafloor and extracting cores of sediment, researchers can read a history of the Pacific written in microscopic shells and chemical signatures. The shells of foraminifera, tiny single-celled organisms that float in surface waters and then sink when they die, record the temperature and chemistry of the water they grew in. The ratio of different oxygen isotopes in their calcium carbonate shells acts as a thermometer, preserving information about past ocean temperatures. Layer by layer, these sediment cores reveal the Pacific's climate history going back millions of years. Scientists can trace ice ages and warm periods when the ocean was more acidic or less, times when circulation patterns were different from today. They see evidence of abrupt climate changes, periods when the ocean's temperature or chemistry shifted rapidly by geological standards, over centuries or even decades. These records show that Earth's climate is not static, but has always been dynamic, responding to changes in solar radiation, volcanic eruptions, continental drift, and the concentration of greenhouse gases in the atmosphere. What these sediment records also show is that the changes happening today are unusual in their speed. Past shifts in ocean chemistry and temperature typically unfolded over thousands of years, giving marine life time to adapt, migrate, or evolve. The current rate of change, driven by human emissions of carbon dioxide, is occurring over decades to centuries, a pace that is geologically instantaneous. This speed gives organisms less time to adjust, ecosystems less time to reorganize, and human societies less time to prepare for the consequences of a changing climate. For thousands of years, people have lived along the Pacific's edges, their lives shaped by the rhythm of its tides, their calendars marked by the migration of fish, their stories woven from the encounter between land and sea. Coastal civilizations rose not in spite of the ocean, but because of it, sustained by the extraordinary abundance that the Pacific offered to those who learned to read its patterns and respect its power. The ocean was not simply a backdrop to human life, but an active participant, providing food, transportation, and connection across distances that would otherwise have remained impossible to bridge. The fisheries of the Pacific have fed more people across more centuries than perhaps any other marine ecosystem on Earth. From the coasts of Japan and China to the shores of Peru and California, communities developed sophisticated knowledge of where and when fish would appear, which seasons brought salmon surging up rivers, when the sardines would swarm in silvery masses near the surface, where the tuna migrated in their endless circuits across open water. This was not casual knowledge, but accumulated wisdom passed down through generations, encoded in songs and stories, refined through observation and experience until it became a kind of science, unwritten but no less rigorous for that. In the Pacific Northwest of North America, indigenous peoples built entire cultures around the annual return of salmon. The fish came in such numbers that rivers seemed to boil with their bodies, millions of them fighting upstream to spawn in the same gravel beds where they had been born years before. The people who lived along these rivers developed methods to catch and preserve salmon that could sustain them through long winters, smoking and drying the fish on wooden frames, storing the abundance of summer for the lean months ahead. The salmon were not just food, but relatives, respected and thanked, celebrated in ceremonies that acknowledged the gift of their return. the health of the people and the health of the salmon were understood to be inseparable, a recognition of interdependence that modern ecology is only now articulating in scientific terms. On the other side of the Pacific, along the coasts of Japan, communities developed similar relationships with the sea. Fishing villages lined every sheltered bay, their inhabitants intimately familiar with the habits of fish, the movement of currents, the meaning of cloud patterns and wind directions. They built boats designed for specific conditions, created nets and traps that balanced efficiency with sustainability, and developed preservation methods that allowed fish to be transported inland to feed populations far from the coast. The ocean was teacher, provider, and sometimes destroyer, and the people who lived beside it learned to live in conversation with its moods, reading signs that told them when to venture out and when to stay safely ashore. In Polynesia, the relationship with the Pacific took a different form, but was no less profound. The ancestors of modern Pacific Islanders became some of the greatest navigators in human history, crossing thousands of kilometers of open ocean in outrigger canoes, guided by stars, waves, and seabirds, carrying with them plants and animals to establish new settlements on islands scattered across the vast blue. This was not reckless exploration, but calculated voyaging, based on deep knowledge of ocean swells, of how waves refract around distant islands, of which clouds indicate land beyond the horizon. They read the ocean the way others read books, finding information in patterns invisible to untrained eyes. But the Pacific did more than sustain local civilizations. It shaped the course of empires and connected continents in ways that transformed world history. When European explorers first ventured into the Pacific in the 16th century, they encountered an ocean so vast it challenged their understanding of geography and navigation. Magellan's crossing took months, his crew surviving on dwindling supplies and facing the constant threat of thirst and starvation as they crossed waters that seemed endless. Yet this difficult passage opened a route that would eventually connect the markets of Asia with the silver mines of the Americas, creating trade networks that circled the globe. The Manila galleons, perhaps the most famous of these connections, sailed annually for more than 250 years, crossing the Pacific from Acapulco to Manila and back again. These ships carried silver from Mexican mines to trade for silk, porcelain, and spices in Asian markets, then returned laden with goods that would be sold across the Americas and Europe. The galleons were floating warehouses, massive ships built to survive Pacific storms, guided by pilots who learned to use the trade winds and currents, sailing north to catch westerlies on the return voyage, their route shaped by the ocean's patterns. This trade made fortunes and bankrupted merchants, connected continents that had never before exchanged goods directly, and created the first truly global economy. The cultural exchange that flowed along these routes transformed societies on both sides of the Pacific. Chinese porcelain became treasured in Mexican churches. Mexican chili peppers made their way to Asian kitchens. Spanish words entered Tagalog, and Tagalog words occasionally filtered back. The Pacific was no longer merely an ocean, but a highway of exchange, carrying not just goods, but ideas, technologies, and the beginnings of a global consciousness that recognized the interconnection of distant peoples. For many Pacific peoples, The relationship with the ocean goes deeper than economics or even sustenance. The ocean is ancestor, the source from which life emerged, the realm of gods and spirits. In Hawaiian tradition, the ocean is the domain of Kanaloa, the god of the sea, and many families trace their lineage back to shark ancestors or other ocean beings. In Maori culture, the ocean is Tangaroa's realm, and the connection to the sea is fundamental to identity and belonging. These are not merely metaphorical relationships, but lived understandings that shape how people interact with the ocean, how they make decisions about fishing and development, how they teach their children to respect and care for marine environments. This spiritual dimension appears in Pacific cultures in countless forms. Coastal peoples, from California to Chile, from Siberia to New Zealand, all have stories that place the ocean at the center of creation, that explain the relationship between humans and sea creatures, that teach respect for the ocean's power and generosity. These stories often encode practical wisdom, such as taboos against fishing in certain seasons or places, allowing fish populations to recover, or warnings about dangerous currents and weather patterns, passed down as narratives rather than technical manuals, but no less effective for that. The ocean appears in art across Pacific cultures, from the intricate designs on Polynesian tapa cloth to Japanese woodblock prints of waves, from Northwest Coast carvings of salmon and whales to contemporary paintings and sculptures that grapple with themes of connection, loss, and environmental change. Artists have long recognized that the ocean is not just scenery, but a presence, a character in its own right, capable of inspiring awe, terror, beauty, and contemplation. To look at these artistic traditions is to see how different cultures have processed their encounter with the Pacific, how they have translated lived experience into forms that can be shared, remembered, and passed forward. And so we come to rest at the end of our journey across the Pacific, this vast ocean that holds within its depths so many stories. Breathe with the gentle rise and fall of swells, letting your chest lift as the water lifts, letting yourself sink slightly as each wave passes, in and out, rise and fall. The ocean's rhythm becoming your rhythm, your breath synchronized with movements that connect you to something vast and ancient and enduring. The Pacific holds you, patient and powerful, asking nothing, offering everything: mystery, beauty, the comfort of belonging to something larger than yourself. We are grateful for this ocean, for its gifts seen and unseen, for the fish it provides and the climate it regulates, for the mysteries it guards and the wonders it reveals to those who look closely. We are grateful for its patience with our mistakes, its resilience in the face of our impacts, its continued presence as teacher and provider despite all we have asked of it. If you've enjoyed this gentle exploration of the Pacific's wonders, we invite you to like this video, subscribe to The Gentle Scientist, and share your thoughts in the comments below. Your support helps us create more journeys through science, more moments of calm. But for now, let the Pacific cradle your thoughts as you drift towards sleep. Let its depths hold your worries. Let its rhythm carry you into dreams. Rest well. Good night.